Okay. Yeah, very good morning, my dear students. Yesterday's class, I think we were discussing regarding the two important concepts. One is compound bars or a composite bar, and second one is the temperature stresses. Okay, let us for 2 or 3 minutes let me just quickly review the things what we have done in the last class. So by the time others to join, right? So in the last class, I think we were discussing regarding the compound bars. A compound or a composite bar is a one which is made up of two different materials. Okay, and their ends are fixed, rigidly fixed. Okay, so when it has been subjected for an external load, it undergoes a deformation. So the two important points that you should remember in the case of a compound bar is the deformation in the both the bars will be same. In the sense, deformation in the material 1 or a bar 1 is equal to the deformation in the material 2 or a bar 2. Okay. And the second important thing is the load, the total load carried by the entire composite bar will be shared by the two materials or a two bars, not equally, shared by the two materials. So therefore, what we can say here is the total load acting or total load applied over a composite bar is equal to the sum of the loads shared by the individual bars or individual material. So these are the two important things that you're supposed to remember when you are analyzing a compound bar or a composite bar. Right, and based upon the two important equations what last class we discussed, so making use of this we can determine the stresses and the strains that will be induced within the composite bar due to the application of an external load, right? So that is the one what we were discussing in the yesterday's class, and afterwards I think I just given an introduction to the thermal stresses or a temperature stresses. So this thermal stress or a temperature is basically when a material is prevented to undergo a free expansion due to a change in temperature, the stresses will be induced within the bar or within the material, and those stresses we call it as we will call that as a temperature or a thermal stresses, right? So and also the free expansion is a function of the coefficient of thermal expansion or coefficient of linear expansion and the length as well as the change in temperature. So therefore, the free expansion, we have got an expression in the form of an alpha into delta T into L, where alpha corresponds to the coefficient of linear expansion or a thermal expansion, and it is having a unit per degree centigrade. And the second important thing is that second term is the delta T. Delta T is the change in temperature and L is the length, right? So when you prevent the bar to undergo a free expansion due to change in temperature, these stresses will be induced, and these stresses we call it as a temperature stresses, right? And these stresses are compressive in nature when there is an increase in the temperature, since we are restricting or we are constraining or preventing the bar to undergo a free expansion by providing an unyielding support, or we can say it as a rigid supports. Okay, and similarly, conversely, if I take the temperature is decreased, okay, so again when the temperature is decreased, so the material will undergo or means it is prevented from undergoing a free expansion, and hence the nature of temperature stresses induced within a bar will be tensile in nature. So these are the things what I was talking in the yesterday's class. Also, I think we go ahead with one step for calculate how to calculate these temperature stresses in the single bar. Okay, bar which has been subjected for a change in temperature. Okay, let us just quickly review that, and afterwards I will take you for the temperature changes or temperature stresses in a compound bars. Okay, yeah. Yeah, this was what I was talking in the previously. So this is a single bar. A single bar was the length is L, capital E is a modulus of elasticity, and alpha is the coefficient of linear expansion of a diameter D. And when it is undergoes a change in temperature, of course, both the ends of the bar is been fixed. So when it undergoes a change in temperature of delta T, so we can say what is the compressive strain in the bar. So thermal expansion is given by alpha into delta T into L. and the compressive stress in the compressive strain in the bar is alpha into delta T into L divided by L. So compressive strain, what you will going to get, it is alpha into delta T. So by using the Hooke's law, so we can easily say the compressive stress, we can calculate or we can relate compressive stress as alpha into delta T into E. So therefore, hence the thermal stress induced in the bar is equal to alpha into delta T into E. This is the expression I think we discussed yesterday's, and I think I stopped at this point in the last class. Okay. So this is the calculation or the determination of a temperature stress in a single bar undergoing a change in temperature. So which you can calculate by using an expression alpha into delta T into E, where alpha is the coefficient of linear expansion, which will be unit will be per degree centigrade, whereas delta T, it is the temperature difference or change in temperature in degree centigrade, and E is the modulus of elasticity of the material of the bar, which is in Newton per millimeter square or in megapascals, whatever it might be, right? So this is what we were discussed in the yesterday's class. Okay. In today's class, let me take you for the most important concept, what we call it as temperature stresses in a composite bar. So we discussed a bar undergoing a change in temperature. Okay. So in today's class, I will just take you for a composite bar, how the composite bar behaves, and how to analyze this composite bar when it undergoes a change in temperature. So analysis means it is a determination of stresses and strain in the corresponding bars, right? So let us just consider a composite bar. See, this is the topic is a temperature stresses in a composite bar. So what we have done here is a composite bar is made of two bars of different materials perfectly joined together so that during a change in temperature change, both bars expand or contract by the same amount. See, this is the material one. Just point option. Yeah, this is the material one, and this is the material two. Okay, so when these two bars, two compound bar, it is two bars made with the two different materials, and they are perfectly joined to their ends, so that when the bar undergoes a change in temperature, okay, change in temperature might be an increase in temperature or decrease in temperature, anything you can assume. So that's why I use the common word as a change in temperature. So this, both the bars will undergo the expansion or contraction by a same amount. Okay, so it is joined in such a way that, right? So now, since the coefficient of expansion of the two bars is different, thermal stresses are developed in the both the bars. So what happens here is, so this is, I told you, this is a two different bars, two bars of different material. So when you say a different material, means it will have their own properties. So therefore, let us take this is a bar one, which is having a coefficient of linear expansion alpha 1, okay, and then modulus of elasticity E1. And similarly for the bar 2, it is alpha 2 into E2, alpha 2 and E2, right? So this is the properties of the material, right? So now when both the bars, or when these two bars constitute a composite bar, and this composite bar undergoes a change in temperature, right? Since both the bars are having a different values of coefficient of linear expansion, these stresses will be induced in both the bars. So those stresses, we call it as a temperature stresses, right? Now our task is how to calculate or how to determine the temperature stresses in both the materials. This is a very important thing for us, because values of alpha will be different for both the materials, and hence we need to get what will be the stress induced, the temperature stress induced in both the material, right? So now what we say, let us take the temperature of the bar is raised by delta T, and let us assume that alpha 1, that is the coefficient of linear expansion of the material 1, is greater than alpha 2. It is alpha 2, right? So now what you are seeing here is alpha 1 into delta T into L. See, this is the amount of free expansion that the material will undergo if the two bars are separated. Let us assume that two bars are separated. Okay, so what is the amount of free expansion that the material will undergo? It is alpha 1 into delta T into L. So this is what the amount of free expansion that the material will undergo due to a change in temperature, right? In the similar way, when you look at the material 2, the amount of free expansion that the material 2 will undergo is given by alpha 2 into delta T into L. So only the parameter that changes is alpha. Because temperature change, delta T will remain same, whereas length will remain same for both the material. Now, so this is the condition, or this is the expression what we use it for determining their free expansion when the two bars are separated. Now let us assume that these two bars are combined together, or they have been bonded together, or they have been joined perfectly together to form a composite bar. And now let us increase, or let us change the temperature by delta T, or let us raise the temperature by delta T. So now what happens in this case? See, since the value of alpha 1 for the material 1 is greater than the alpha 2. So I think you can easily understand here. See, when you take the free expansion of the material 1, if you just calculate, because alpha 1 we are taking delta T and L will remains constant for both the material, only the value will be alpha 1. The parameter is the one which varies will be the alpha 1. Am I right? So here we have assumed alpha 1 is greater than alpha 2. So now the amount of free expansion that the material 1 will undergo will be more than that of the amount of free expansion that the material 2 will undergo. Is it clear, my dear students? Only the value will be variation will be alpha 1, and alpha 1 is greater than alpha 2. So therefore, we can easily ascertain here is alpha 1 into delta T into L, that is the free expansion of the material 1, will be greater than or more than the amount of free expansion that the material 2 will undergo. So it means that the material 1 tends to undergo more expansion or more stretching than that of the material 2. So since the two materials are bonded together here, right? So what we have seen at the beginning is they are perfectly joined such that they both the bars expand or contract by the same amount. So here what happens, this material 2 will prevent, or it starts preventing the material 1 to undergo a free expansion of alpha 1 into delta T. In the sense, what I mean to say here is, so the material 2 itself will act as a constraint or a restraint to prevent the material 1 to undergo a free expansion of alpha 1 into delta T into L. It means, what does it mean? It needs to pull back. It has to pull back the material 1 so that it does not undergo the amount of a free expansion alpha 1 into delta T into L. Is it clear? So when the material 2 offers a resistance for the material 1 to undergo a free expansion, in the sense the material 1 will be subjected for a compressive stress. Please remember this. This is a very important conclusion what we supposed to arrive at the beginning of the analysis of a temperature stresses in a composite bar. The material whose value of thermal expansion, the coefficient of thermal expansion or linear expansion is more, provided delta T and L are same for both the materials, then the material which is having the larger value of alpha will undergo a more expansion, and hence it will be subjected for a compressive stress. Okay, so since we are assuming it as both the material will undergo a same amount of expansion. See, the material 2 is also has been also allowed to undergo a free expansion by delta T, alpha 2 into delta T when they are separated. But when they are compounded or when they are combined, so what happens? So the material 1 will offer the a resistance, or it will make the material to undergo a deformation by an amount alpha delta t into alpha 2 into delta t, and hence the nature of stresses that will be subjected in the case of a material 2 will be tensile stresses. Material 1 is subjected for a compressive stress, whereas material 2 is subjected for a tensile stress. See here, you can see here delta L. I think delta L from here to here we are showing. See, please observe here. Please understand here. Delta L is what? It is the amount of free expansion, amount of expansion that the compound bar will undergo. Got it? So alpha 2 into delta T into L is the free expansion of the material 2, and alpha 1 into delta T into L is the free expansion of the material 1. See, look at the arrow marks over here. In the material 1, so the arrow marks are from right to the left. Right to the left means, so it will be subjected, since it will be pulled back. It has been pulled back so that the amount of free expansion will remain same for delta L. So once it has been pulled back in the sense, so the nature of stresses that will be induced in the material 1 will be compressive in nature. Whereas in the material 2, look at here, the amount of free expansion is this much, whereas delta L will be this much. So this amount of expansion is required for the material to ensure that the total amount of free expansion of the entire composite bar remains constant. So therefore, material 2 will be stretched by this amount from here to here. You can see here. Can you see here? So therefore, you can see the nature of stresses, what it has been induced within the material 2 will be from left to right. It means that the material has been pulled so that the total expansion will remain constant by delta L. So therefore, so final conclusion here is the material 1 is subjected for a compressive stress and material 2 is subjected for a tensile stress. Is it clear, my dear students? If you have any clarification, because this is one of the most important conclusion what we're supposed to arrive at. So if anybody having any clarification over here, you can ask, because if you understand here clearly, then only things will be easy for you. Yeah. Any clarification, my dear students, anywhere?
Sir,
Yeah.
so whose linear expansion will be more, that will undergo compression, and whose
Sorry,
will
sorry.
be less will go expansion.
Yeah. That's what provided delta T and L are same for both the materials.
Same.
Yeah.
Okay, sir. Thank you.
Yeah. Anything, my dear students? Any clarification? Because this is a very important conclusion in the analysis of a temperature stresses in a composite bar. Even if you have a small doubt or a simple doubt, please clarify. This is very important. You should be in a position to understand which material, which bar will be subjected for a compressive stress and which is subjected for a tensile stress.
Sir?
Yeah, tell me.
Sir, I have a doubt, sir.
Please.
Sir, in this, like there are two bars now, sir. So,
Correct.
like at first they'll be at the same length, and once we start heating the bar with the bigger, like the bigger coefficient of expansion will have a greater expansion. So after that, it will get a compressive stress, or like before
Yeah,
only.
say when you
After
separate the
expansion,
over.
yes, sir.
Okay.
Yes, sir. Yes, sir.
So when you take the two bars separately, don't take it as a composite bar. Take it separately.
Okay.
Okay. So what is the amount of free expansion that the material 1 or a bar 1 will undergo is calculated by alpha 1 into delta T into L. Am I right?
Yes, sir.
Is it clear, Abhishek?
Yes, sir.
Okay. Similarly for bar 2. So what is the free expansion it undergoes is alpha 2 into delta T into L.
Yes, sir.
When you take it separately, don't combine, or they don't make it compounded separately. Okay. So now what we do is we will combine both the materials or both the bars.
Okay, sir.
We'll combine in such a way that the total amount of free expansion both the material will undergo will remains constant. We will fix in such a way that.
Okay, sir.
That is what we got it as delta T into L. Sorry, delta L into T. That's what we have got. Am I right? Right?
Yes, sir.
Delta L. Sorry, delta L. I'm sorry. Delta L. Delta L I'm showing here, right? Delta L
Yes.
is the total amount of free expansion that the entire composite bar will undergo.
Okay.
Okay. So now, if you just
Yes.
combine the two bars of different material, okay, so the material which is having larger value of alpha 1, okay, it undergoes,
We'll have a compressive
it undergoes more expansion. Okay, so if you look at here, alpha 1 into delta T into L, this is from here to here, am I right? From here to here, this one. When you look at delta L, this is which is delta L is less than alpha L1 into delta T into L, am I right? Can you see from the diagram over here?
Yes, sir.
So what happens if I want to make the material want to undergo only this much amount of delta L means, so it needs to be pulled back, am I right?
Yes, sir.
Means the nature of stresses that should be induced within the bar 1 should be compressive. Means you need to contract this much amount of expansion so that the total amount of free expansion will remain same with respect to the material 2 also.
Yes, understood, sir.
Okay. Similarly,
Yes,
for material 2. So material
Yes,
2, what happens? Alpha 2 into delta T is this much, and it needs to be extended this much. So therefore, the tensile stresses will be induced in the material 2.
Yes, sir. Thank you, sir.
Got it? Yeah.
Yes.
Yeah. Any clarification, my dear students? Anybody? Feel free. Don't hesitate to ask the doubts because clarifications will be there. Definitely it needs to be, because temperature stresses are very important for you. Definitely 3 to 4 marks it will be there in the gate examination on temperature stresses. Basic concept. Any clarification from anybody? If you have any clarification you can make, otherwise I will go for the continuation. Shall I continue?
Yes, sir.
Right. Yeah. Next is, once we have got the nature of stresses that will be induced within the two bars. So that conclusion here is based upon the value of alpha 1, alpha. So the material which is having the larger value of alpha, provided delta T and L remains same for both the materials or both the bars, that material will be subjected for a compressive stress, and the material which is having the lesser value of alpha 2 will be subjected for a tensile stress. So please remember this, but the condition is delta T and L should be same for both the materials, right? So this is what they have given, the just it is in the mathematical form: free expansion in the bar and free expansion in the bar 2. Since the both bar expand by delta L together, we have the following conditions. Look at here. Delta L is less than alpha 1 into delta T into L. Am I right? That's what we have shown in the figure there. The bar gets compressed, resulting in compressive stress. Okay. Similarly, bar 2, delta L is greater than alpha 2 into delta T into L. The bar gets stretched, resulting in a tensile stress. This is what I was just explaining in the previous slide. Now let us just move on to how to write an expression for the, see, once told it is subjected for a compressive stress and tensile stress, the nature of strain that will be induced within the two bars, material 1 will be compressive strain, and in the material 2 will be tensile strain. Am I right? I think you can understand this, right? Now let us write an expression for a compressive strain in the two bars. So we have taken here a compressive strain in the bar 1 and compressive strain in the bar 2. Okay, this is a bar 1. So let us write alpha epsilon 1, sorry, epsilon 1. Epsilon 1 is the strain that will be induced in the bar 1. Since the stress induced in the bar 1 is compressive, the strain is also a compressive. Am I right? So compressive strain in the bar 1 is equal to epsilon 1 is equal to alpha 1 into delta T into L minus delta L. See what is this? You can see, can this, the amount of contraction that the bar one will undergo. The amount of contraction, why I'm talking about here, the free expansion of the bar one is more than the actual total expansion of the entire composite bar. So therefore, this expression, when you're looking here, alpha 1 into delta t into L minus delta L. So what does this numerator term represents is the amount of contraction that the bar 1 will undergo. The amount of contraction, this is what we call it as a deformation in a bar 1. So amount of contraction or deformation in a bar 1 divided by L, so original length. So this will constitute the compressive strain in the material 1. Similarly, tensile strain, since the bar 2 is subjected for a tensile stress, right? The nature of strain that will be induced in bar 2 will be tensile. So the tensile strain in bar 2 is an epsilon 2. So here it is the numerator, it is a ratio of the deformation, the amount of elongation that the material 2 will undergo. So the amount of elongation, look at here, delta L minus alpha 2 into delta T into L by L. So this numerator term will represent the amount of elongation that the material will undergo. So nothing but the deformation in the material 2. So divided by L, this will give the tensile strain in the material. Okay, so now when you add these two, epsilon 1 plus epsilon 2, which you are going to get it as alpha 1 minus alpha 2 into delta 2. Got it, my dear students? How you can writing over this expression here? The total strain in the material 1 and 2, this will constitute the total strain in the composite bar. So epsilon 1 plus epsilon 2, when you add these two equations, the resulting expression will be alpha 1 minus alpha 2 into delta 2. Okay.
Sir, I have a doubt.
Yeah, tell me.
So why did you subtract delta L and answer?
See, this is, I think, previous diagram. See here. You see here?
Yes.
Diagram. See, what's happening here is, see, this is delta L, am I right?
Yes, sir.
Okay, this is alpha 1 into delta T into L. Am I right?
Oh,
So
yeah,
how much amount of deformation that the material 1 will undergo from here to here only?
Okay, okay.
Yeah, I just look at the movement of my pointer here. So from here to here is the amount of deformation that the material 1 will undergo.
Okay.
So how to calculate this distance will be
Subtract that by
alpha
delta.
1 into delta T into L minus delta L. Am I right?
Yes.
So that will constitute the amount of contraction that the material 1 will undergo is nothing but the deformation in the material 1.
Okay.
Got it? Similarly for material 2. Material 2, just observe here.
Yeah.
See, from here to here I want. This is a deformation that the material 1 is going.
Okay.
It is nothing but delta L minus alpha into delta T into L. So because it is subjected for a tensile strain. It is stretched and this is contracted.
Okay. Okay.
Look at the arrow marks, arrow directions here. This is tensile and this is compressive. Is it clear?
Yes.
So this is the expression what we have got here. So epsilon 1 and epsilon 2 we have got it. And when you add these two strains, so you will going to get an expression for what is the total strain in the material 1 and 2, or we can say it is in the composite part, right? So alpha 1 minus alpha 2 into delta T. So this is epsilon 1 plus epsilon 2, right? Now let us take, let sigma 1 and sigma 2 be the temperature stresses in the bars. The above equation can be written as, above equation in the sense, so epsilon 1 can be written as in sigma 1 by E1. Am I right? So by using Hooke's law. So we know sigma is equal to E into epsilon as per the Hooke's law. So now I am writing it for the epsilon. So epsilon will become sigma by E. So since it is for the material 1, I am just giving a suffix 1 over here. So sigma 1 divided by E1 plus sigma 2 by E2 is equal to alpha 1, because see here, alpha 1 minus alpha 2 into delta T. Is it clear, my dear students? This expression, this is very important conclusion in the analysis of a temperature stresses in a composite wall. Any clarification till here? So you can ask. Anybody? Yeah. Any doubts, my dear students? Anybody having any clarification over here? Because understanding of a composite bar is a little difficult, but still more important thing for you. Very, very important for you. No clarification? Shall I continue?
Yes, sir.
All right. So if wherever you find it difficult or to understand, please stop me there only. Okay. So we will just continue. We will just clarify your doubts and I will just continue. Right. So now we have got this expression. This is one of the most important expression in the analysis of a temperature stresses in a composite wall. So please remember this: sigma 1 by E1 plus sigma 2 by E2 is equal to alpha 1 minus alpha 2 into delta T. This is the one expression which is required for us in the analysis of temperature stresses in a composite wall. Please make a note of this, equation. Now, I will just move on to the next one. So what happens in the previous expression? See, you will be knowing alpha 1, you will be knowing alpha 2, you will be knowing delta T, and E1, E2 will be given. But there are two unknowns over here, sigma 1 and sigma 2. Both are not known for us. We need to determine these values. So alone this equation cannot be used to calculate sigma 1 and sigma 2. Why? Because there are two unknowns here. One is sigma 1 and sigma 2. Okay. To calculate this, we need another one equation, what we generally call it as a compatibility equation. Okay, so to get this equation or to determine the temperature stresses in the composite bar made up of two different materials, so this is the one equation we are going to use, and we will use another one equation. Without only with one equation, it's not possible to get the solution over here, right? So what is another one equation here is, let us take, in the absence of external forces. See, we are not applied any external forces to the composite bar. So there is no 20 kilonewton or 30 kilonewton load has not been applied externally. Only we are talking about temperature stresses due to a temperature change. Am I right? So therefore, in the absence of external forces, for the equilibrium condition, the compressive force in bar 1 should be equal to tensile force in bar 2. Please remember, this is another one equation which is required for us to solve or to determine the values of sigma 1 and sigma 2 over here. Right. So in the absence of external forces and for equilibrium condition, the compressive force in bar 1 should be equal to compressive force in bar 2. Right. So how do we write a force? Force can be written in the form of stress multiplied by its cross-sectional area. Okay, so because stress is nothing but a load divided by the cross-sectional area, and hence the force can be written, or a load can be written as the stress multiplied by corresponding cross-sectional area. Am I right? So therefore, so using this condition, so this equilibrium equation, this condition leads to the following equation. So compressive force in a bar 1 can be written as sigma 1 into A1, which is equal to sigma 2 into A2. So this is the another one equation which is very useful for us in calculating the values of sigma 1 and sigma 2. So how we can make use of these two equations? Say the previous equation I told you, this is the one equation. Am I right? So this is the one equation. And second one is, this is the equation. If sigma 1 into A1 is equal to sigma 2 into A2, this is another one equation. So how we can make use of this expression means, see, in this expression, we can write what is sigma 1. Am I right? Sigma 1 is equal to sigma 2 into A2, and I will take A1 to the denominator. So I can express sigma 1 in terms of sigma 2. Am I right? So where you are going to get sigma 1 is equal to sigma 2 into A2 by A1. Now what I do here is, I will take this, I will substitute sigma 1 as sigma 2 into A2 by A1 in the previous expression, in this equation. So now what happens? In place of sigma 1, I will be writing as sigma 2 into A2 into E2. Sorry, A2 into A2 by A1. I'm sorry, A2 by A1. Sigma 2 into A2 by A1. Right. So now only the unknown term in this expression at that time will be sigma 2. So we can easily determine what is sigma 2. And once we get sigma 2, then making use of this expression, we can get what is sigma 1. So this is how generally we analyze the temperature stresses in a composite pipe. Is it clear, my dear students? Is it clear?
Yes, sir.
Any clarification over here, please? Because this is very important, not a matter if I take 1 or 2 hours extra for this composite temperature stresses, because very important for you. First, you have to understand, definitely one problem for 10 marks will be there on temperature stresses. I want you people to understand the concept clearly and how you can apply those concepts later, what I will go to discuss. Yeah. Anything, my dear students? Ashit Kumar,
Yes, sir.
any clarification, Ashit?
No, sir.
Got it? Everything clear?
Yes, sir.
Okay. Harsha Ayappa.
Yes, sir.
Yeah. Harsha, could you have any clarification, Harsha?
No, sir.
Okay. Rahul Rathod,
Yes, sir.
understood the concept of temperature stresses?
Yes, sir. Understood, sir.
Any clarification, any doubts?
No, sir.
Vasant Kumar?
Yes, sir.
Yeah, any clarification, Vasant?
No, sir.
Okay. Vinod,
Sir.
are you there?
Yes, sir.
Yeah, understood.
Yes, sir. Understood, sir.
Any clarification from anybody, you can ask. This is very important concept. That's what I'm just asking you. Okay. So if you don't have any clarification, let me move on to the next one. So yeah, you can see here, if the temperature of the composite bar is reduced, see what we are talking throughout the concept of composite bar, you are raising the temperature. So temperature has been raised. So if the composite bar, temperature of the composite bar is reduced, so it will be totally a converse. Please remember this. Then a tensile stress will be induced in bar 1 and compressive stress will be developed in bar 2 since alpha 1 is greater than alpha. Could you able to understand over here? This is a very important conclusion you have to remember. See, what I have just discussed is when the temperature is raised. Raised means you are increasing the temperature. So when you increase the temperature, because of the value of alpha 1 is greater than alpha 2, material 1 is subjected for a compressive stress, whereas material 2 is subjected for a tensile stress. If you conversely, if the temperature is reduced, okay, so you should be very careful while you are solving or when you are analyzing. Okay, so when the temperature of the composite bar is reduced, then a tensile stress will be developed in the bar. So what happens when temperature is reduced? So the material will start contracting. Okay, so it needs to be pulled out to get a exact total amount of deformation. In the similar way, what happens in the case of a material 2, material will to undergo free expansion and it needs to be pulled back so that it will get contracted. So this is what you should be very careful. Look at the question whether you need to temperature is raised or temperature is reduced. So based upon that, you should be in a position to conclude whether which material is subjected for a compressive stress and which is subjected for a tensile stress. and look at the value of alpha 1 and alpha 2, and also look at whether the delta T and L will remain same for both the materials. Is it clear, my dear students? This is a very important conclusion what I wanted to convey at this point, because very, 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 very important here. Is it clear?
Yes, sir.
Yes, sir.
Okay. Okay. So I will just stop at this point. It's already 9:16. So I will go back. We'll go back to the Google Classroom. So please attend the quiz over there. Okay. And once you submit the quiz, and you can go back to the, you can go to the next class. Okay. I will continue the same thing in the Monday's class. Okay. So please type your USN in the chat box. Okay. And attending the quiz is mandatory for everybody. Okay. Let us move on to the Google Classroom. Yeah, quiz is assigned in the Google Classroom. I want everybody to just attend the quiz and submit it, and you can switch over to the next class. Okay, I will meet you in the next class. Thank you.